In our previous lecture, we have discussed in detail about the nuclear shell model, and then we have discussed its 1 and 2 application, and that is how we can find out the spin and the parity of a given nuclei. So, in continuity to the previous lecture, in this today's talk, I would like to explain how we can find out the nuclear magnetic moment. So that is different for jackknife case and the stretch case, and further we will discuss about the electrical quadrupole movement, and then we will discuss what are the major limitations or what are the major failures of shell model, and how the other models like the nuclear collective model and the Nielsen model, so they come into line, and they explain the points which shell model unable to explain. So starting with this lecture, so nuclear magnetic movement. So nuclear magnetic movement is the movement of an atomic nuclei and which arises from the spin of protons and neutron, and mainly this is the magnetic movement, and that is dependent upon the angular momentum, that is the azimuthal quantum number and the spin quantum number. I would not go in detail about the derivation of this nuclear magnetic moment, but you can check from these calculations that this magnetic moment, it is sum of the angular magnetic moment and the spin magnetic moment, and from that we can find out the value of this gyromagnetic ratio, that is the total gyromagnetic ratio, which is depending upon the angular gyromagnetic ratio and the spin gyromagnetic ratio, and the value of this G. So this is different for protons and different for neutrons, and basically it is dependent upon the last unpaired neutron or proton which is present in the closed shell. And you can see from this slide that for protons, so this is the value of this Gg, and once we find out the value of this gyromagnetic ratio, and from that we can find out the total magnetic movement. So I will write it here, the formula. So this is the magnetic movement which is happening due to the magnetic field which is being generated by protons and neutrons, and which is acting along the z-axis, and this is value this value we have to find, and it is dependent upon the value of Gg, and J is our total angular momentum, and mu, and that is the nucleon magnetron. So these values you have already found. So once we find out the value of Gg, and this Gg, that is basically dependent upon the angle which the spin angular momentum making with the total angular momentum, or the azimuthal quantum number which is making with the total quantum number. So basically it is due to the JJ coupling, or how these total angular momentum which is being generated due to the value of L and S. So these are the values of the magnetic moment that is acting along the z-axis, and for last unpaired nucleon, and the value of this GL, that is if there is a proton which is in the outermost shell, then we will choose this formula, and if there is a neutron in the outermost shell, and then we will choose this formula. Basically there are two values of magnetic moment which we will derive. So one is when the value of total angular momentum which is equal to L plus S, and the second when we find when it is equal to L minus S. So this case, when it is having the maximum angular momentum, so that is known as the stretched case. And this case, that is known as the jackknife case. So these are the values of the magnetic moment for the stretched case, and similarly you can find out the magnetic moment for the jackknife case. So these are some of the formulas which you need to remember. And once you put on the values of this J, so that we can find out from the ground state spin of the nuclei. So mu n, that is the nuclear magnetron, this value we know. So from these we can find out the magnetic moment depending upon whether the last unpaired nucleon, it is a proton or it is a neutron. And second, we have to check whether it is following J, that is equal to the stressed case, or it is following the jackknife case. So just checking these 2 points, so then we can successfully find out the magnetic moment of a given nuclei. So based on the value of this magnetic moment with respect to total angular momentum, so we have plotted these 2 values. So this is the case for the stressed case, and this is the line which is representing the minimum value of the magnetic moment for protons, and that is the jackknife case. And similarly, we can plot out the magnetic moment in a graph, and it is representing the maximum and minimum magnetic moment, which is dependent upon the value of J. So experimentally, it has been observed that the most of the atomic nuclei whose magnetic moment, it is lying within these 2 line limits, and these line limits they are showing, and these lines they are known as the schematic lines or schematic curves. So this is a famous scientist, Schematic. So he published a paper in Physical Review later, and he find out that based on these 2 values of the jackknife and stressed case, we can experimentally relate the values of this magnetic moment for different nuclei. And similarly, these 2 values or these 2 lines, so most of the atomic nuclei whose magnetic moment lying within these the line limits. So these are the formulas which you need to remember. So this is for proton. You can see that the magnetic moment, it is having a positive value, and this is for neutron, and you can see that the magnetic moment, it is having almost a negative value for this neutron. Now this negative value of magnetic moment for neutron, now what it is representing? So it is representing that a negative magnetic moment of a neutron tells us that neutron is a complex particle containing negative and positive charges in equal amounts, and that the negative charges on the average farther from the axis of this axis of rotation. So neutron, it is a more complex particle as compared to protons. So the neutron, it is having a negative magnetic moment, while the proton, it is having positive magnetic moment in most of the cases. So let us try to find the magnetic moment of these 2 nuclei for carbon and sodium using this nuclear shell model. Now here, if you look in this carbon case, so in carbon there are 6 protons and 7 neutron. So since proton, it is a even nuclei, so it is completely paired up, so we will not consider in this magnetic moment participation. So the particle which is obeying or which is participating in this magnetic moment, that is the last unpaired neutron. So using the shell model, so which I have explained you in the previous lectures, so first 2 nucleons, it will be in 1s 1 by 2, then 4 nucleons, they will be occupied in 1p 3 by 2, and the last neutron, it will be occupied in 1p 1 by 2 orbiter. So from this you can see that the value of J, it is equal to 1 by 2, and this neutron, it is present in the p orbital. So p orbital means the value of L, that is equal to 1. Now we have to relate these 2 values. So as we know that neutron and proton both are fermion, they are having the half integral spin. So J value, it should be equal to 1 by 2 from this, and it comes only when it is having L minus S case. because L is 1, S is 1 by 2, and from this we can find out the value that is coming equal to 1 by 2, as you can see above. So this is a case of jackknife. So for jackknife case, if the last particle is neutron, then we have to follow these formulas of magnetic moment. So for L minus S case, we will consider the magnetic moment will be equal to 1.91 J over J plus 1 times the nuclear magnetron. So putting the value of J in this formula, and we can find out the magnetic moment of this carbon 613 atomic nuclei. So similarly, you can find out the magnetic moment for this sodium 1123. So here you can see that there are 11 protons and 12 neutrons. So neutron, it is an even number, it will not participate in the magnetic moment due to the complete paired up particles. So proton, it is having a odd number, and you can see that using the shell model, 2 nucleons, it is being filled in 1s1 by 2, then 4 nucleons, it is being filled in 1p3 by 2, then 2 nucleon, it is being filled in 1p1 by 2, and the last 3 nucleons or the last 3 protons, it will be in 1d5 by 2. So from this, the value of J, it is coming 5 by 2, and it is present in d orbital. So for d orbital, L is equal to 2. So S is 1 by 2. So this is a case of JL plus S case. So JL plus S, that is the stretched case. And for stretched case, if the last particle, it is a proton, and you can see that the magnetic moment whose value is J plus 2.29 times the nucleon magnetron. So putting the value of J, and we can find out the magnetic moment of this sodium 1123 atomic nuclei. So this is how in order to find the magnetic moment of a proton or neutron, you first need to find the value of this J, and then you have to check whether it is a stretched case or it is a jackknife case, and on the basis of that, you can use that particular formula for magnetic moment, and you can find out the magnetic moment of the given nuclei. So next is the quadrupole movement. So this quadrupole movement, it measures the deviation from the spherical system. So if the nucleus, it is a complete sphere, then its quadrupole movement is 0, and the quadrupole movement for even nuclei using this shell model, it comes out to be equal to 0. And later they have found that for even nuclei, the quadrupole moment is not always 0. So shell model also fails here, because it says that for even nuclei, the quadrupole moment is 0, but according to collective nuclei, it says that it is having some deformed nucleus, and that nucleus having high atomic number of protons or neutrons, it is no longer a complete spherical nuclei, and there is some sort of vibrations or deformations or rotations which is being happened between the presence of due to large number of protons within the nucleus. So for odd even or even odd nuclei, so this model or this formula, it is quite successful in order to find the quadrupole movement. So it says that quadrupole moment, it is minus 2j minus of 1 bracket over 2j plus 2 into r square, where j, that is the total angular momentum, and r, that is representing the mean square radius of the given nuclei. And basically this r square that we can use is equal to 3 by 5 r square, and our formula for quadrupole movement, it becomes something like this, where rc, that is equal to the critical radius, and the value of this RC it comes, or we generally use, that is equal to 1.2 A 1 by 3, where A is representing the atomic masses, and depending upon which atomic nuclei we are talking about, and we can find out the critical radius of the given nuclei, and from that we can find out the quadrupole moment. Now if you check in this formula, so there is a negative sign here. So this negative sign, it is representing that in majority of the nuclei, the quadrupole moment, it comes out to be negative. But here this model, or this shell model, it failed because they have seen that in majority of the atomic nuclei, or in higher number of nuclei, the quadrupole moment, it is having a positive value. And later on they designed that the value of Q, when it is 0, so then we consider that nucleus, it is a spherical body. When Q it is having a negative, then we generally consider that nucleus as the oblate nuclei. Oblate nuclei, it is something like a egg-shaped nuclei. And the quadrupole movement, when it comes out to be positive, then it is known as a prolate nuclei. And prolate nuclei, it is something like this vertical. And basically it is dependent upon the major and minor axis A and B. So if the value of this major axis it is greater than the minor axis, then we generally consider it as a oblate nuclei. And if the value of this major axis it is less than the minor axis, then generally we consider it as the prolate nuclei. And generally we can also find out the quadrupole moment from this major and minor axis. One of the formula in order to find the quadrupole moment is something like this as well. Now here in this example, you can see that for 7 nitrogen 15, the quadrupole movement, and you can see that here there are 7 proton and 8 neutrons. So it is no longer a even nuclei, because it is a even odd nuclei. So there are even number of neutrons and odd number of protons. And when you find out the value of J for this case, so the last unpaired proton, it is present in 1p 1 by 2 orbital, and from that you have calculated the value of J, so it is coming out to be 1 by 2. And using the previous formula, so this one, so when we put the value of this J, that is equal to 1 by 2, and the value of Q, it comes out to be 0. Now when Q comes out to be 0, so then it should be a completely spherical nuclei according to shell model. But it has been observed that, so this is no longer this is not a spherical nuclei. So these are some of the limitations of shell model. So because the shell model, it failed to explain the exact values of this quadrupole movement. And when the people, they found it experimentally, they found that the predicted values are very high as compared to these theoretical values, which are negative or 0 in most of the cases. So this is the drawback of this shell model. So it failed to explain the exact values of this quadrupole movement. So this is how you can find out the electrical quadrupole movement. So even if the question it comes sometimes in the competition exams, so find the electrical quadrupole movement using the shell model, then you have to use this formula, so which I have explained to you. So first you have to find the value of J. So like for example in this oxygen 817, so we can find the value of J, which is due to this last unpaired neutron, and J it is coming out to be 5 by 2, and from that J you can find out the value of this critical radius. So this critical radius, that is equal to 1.2 into A1 by 3. So here A, that is the atomic mass of this oxygen nuclei, that is 17. So from that we can find out the value of this critical radius, and putting these values of critical radius and J, you can find out the value of this quadrupole moment, and this is equal to minus 0.326 bar. So here the units to measure quadrupole movement. So the quadrupole movement, it is generally measured in barns, and 1 barn, so that is equal to 10 raised to power minus 28 meter square. So this is how you can find out the electrical quadrupole movement for the given nuclei using this shell model. So what are the various points which explain about the success of shell model? So shell model, it successfully explain about the existence of magic number and their stability. So second, the shell model provides the correct explanation for the ground state spin and the magnetic moment of most of the nuclei. And the third is it successfully explain about the nuclear isomerism. So the nuclear isomerism, so that is the existence of the isobaric or isotomic nuclei. So that is present in particular energy range. So that is why some nuclei which is having large number of nuclear isomerisms as compared to their neighboring nuclei. So these are some of the success points of this shell model. So they successfully explained, and so they successfully explained about this nuclear isomerism. So they are generally also known as islands of isomerism. So shell model, so they explain that, so if we plot out the number of neutron or proton with respect to number of isobars or isotopes, so you will see that, so there are majority of the bars or number of isotopes which are present in the range of 40 to 82. So shell model successfully explains so why these nuclei, they are having larger number of isobars as compared to their neighboring nuclei, and that is based upon the excited states or the first excited states of these given nuclei, so as compared to their neighbors. So some of the limitations of shell model, so shell model do not correctly tells us about the ground state spin. So there are some exceptions. For example, the shell model, it did not correctly explain about this nuclear spin of 1123, and if you find out the ground state spin and parity, and according to shell model, its predicted value is J5 by 2, but experimentally they have found that its correct value is 1 by 2. So similarly, there are some other nuclei, so which shell model failed to explain why their nuclear spin that is different as compared to the arsenic nuclei. So the another example is arsenic 33-7 nuclei. So according to shell model, its spin, it should be equal to 5 by 2, but the experimental value, it is coming out to be 3 by 2. So there are many other nuclei, so like the rubidium, Ru101, cadmium 109. So shell model failed to explain their correct ground state spin. So although in majority of the cases, in 90% of the cases, shell model successfully explained the ground state spin and parity of the nuclei. So second point, shell model failed to explain this odd nuclear spin. So this I have already told you. So odd spin we can find out using the Nordam rule. So we sum up all those values Jp plus Jn plus Lp plus ln, and if these values are coming out to be odd values, then we will consider some cases Jp minus Jn, and if it is coming even value, then we will apply the different cases. So for odd nuclei, so this has been explained using this Nordam rule. So shell model failed to explain the ground state spin of this odd nuclei. So shell model, it failed to explain the first excited states of even nuclei. So they are coming different as compared to their experimental values. So these are some of the limitations. So where shell model get failed, and that has been cope up or covered by another model that is known as the collective model. So that we will discuss once we will do these 2 or 3 important numericals. Now if you look at this question, so it is saying that in the nuclear shell model, the potential of model as is given by this value, the correct spin and parity and isospin assignment for this carbon C1613 is. So we have to find out this spin and parity of this carbon 613. So this you can easily find. So it is 1s1 by 2, 1p3 by 2, 1p1 by 2, and 2 nucleons will go here, 4 go here. So proton number is 6, neutron is 7. So last unpaired neutron, it will be in 1p 1 by 2. So J will be equal to 1 by 2, and since it is in the p orbital, so it is having inactive parity. So second, we have to find out this isospin. So this isospin concept, it has been explained by the independent shell particle model. So this isospin we generally find out. So isospin is basically is implemented to those nuclei which is having the same atomic mass but having different charges. So for example, we apply the concept of this isospin to all those particles which is having the same nuclear mass or same atomic mass but having different charge. For example, neutron and proton, they are having the same mass but having different charge. So similarly, we apply the concept of this isospin to electron or to positron, or we also apply the concept of this isospin to quarks or to muons, so which are positive muons, negative muons, or neutral muons. So this isospin concept is applied to all those particles which tells us about their charge state. So this isospin, this tells us about this charge state of particle. So I will not go in detail about this isospin concept. So here, how we can find out the isospin of this carbon C16 nuclei, and the formula to find out this isospin is, so let me erase this to make some space. Okay. So spin we have calculated, it is coming 1 by 2 minus, and we have to find the isospin. So isospin we generally find out with the formula 1 by 2 Z minus N, where Z is representing the number of protons and N is representing the number of neutrons. So here in the above case, in carbon 613, so there are 6 proton and 7 neutron, and so this comes out to be minus 1 by 2. So this is one way to find out the isospin. So second way to find out the isospin is using the multiplicity or the degeneracy of the given particle. So this is isospin is equal to multiplicity m minus 1 by 2. So this multiplicity we generally find out, or we generally say it as the degeneracy of the given particle. So that is equal to 2j plus 1. So multiplicity we find out with 2j plus 1. So j is equal to 1 by 2. So this multiplicity comes out to be equal to 2. So 2 minus 1 by 2. So here it is 1 by 2. So here I would like to mention we also have to add the parity here. So the parity we multiply with this. So the parity coming out for this is minus. So we will add minus sign here. So the isospin for this carbon 613 nuclei will be equal to minus 1 by 2. So the correct option is 1 by 2 minus and minus 1 by 2. So option A is the correct option. So sometimes they ask you to find out the isospin as well, because we know that the nucleons, so the nuclear forces, they are dependent upon various type of exchange forces. So like the total wave function, it is dependent upon the space coordinate r1, r2. It is dependent upon the spin coordinate, polyspin operator sigma 1, sigma 2, and it is dependent upon the isospin coordinate tau 1 and tau 2. So these nuclear forces, it is dependent upon generally the three type of coordinates. One is the position coordinate. So you have studied in the exchange forces, various type of exchange forces which occurs in the nucleus. So other is the spin coordinate, and third is the isospin coordinate. So this isospin, it also plays a great role in order to find out the exact spin or exact total angular momentum of the given nuclei. So next question is, find the total angular momentum and parity of this sulfur nucleus using the shell model, and also find the electrical quadrupole movement from this collective model or using the shell model. So here you can find out using the shell model. So like in sulfur 1633, so there are 16 proton, so they are even, so it will not play any role. So the magnetic the total spin, it will be due to this number of last unpaired nucleons. So the last unpaired neutron, it is in 1d 3 by 2 state. So J comes out to be 3 by 2. So it is in the d orbital. So parity will be equal to even parity. So ground state spin, it comes out to be 3 by 2 plus, and using the formula which I have explained to you already, you can find out the quadrupole movement. And once you find out the value of this ground state spin, putting the value of this J and R naught, so R naught is equal to 1.2 into A is here 33. So you can also find out the value of this R naught, and you can find out the value of this electrical quadrupole movement. So this is how you can find out various magnetic movement, quadrupole movement, ground state spin, and parity of the given nucleus. So next type of questions which can be asked in the competition exam. So this is the question of the NET June 2016 examination. So we have to find out the nuclear magnetic moment of aluminium 1327. So the value, so here you can see that neutron, it is even number, so the spin will be due to the last unpaired proton, and it comes out to be 1d 5 by 2. And so this is a case of JL plus S case, and for proton we have to use this formula, J plus 2.29 times the nucleon magnetron. and from that you can find out the nuclear magnetron. That comes out to be 4.79. So correct option is option C. So another type of questions, so they can ask you to find the value of this gyromagnetic ratio. So what is given? So we have given the formula of this magnetic moment. So I will write it here. E h bar over 2 mc g into j. So this is known as the nuclear magnetron. So what is given? The spin gyromagnetic ratio, and for proton and neutron it is given, and for oxygen 817. So once we will find out the value of ground state spin, and j it is coming out to be 5/2. So it is present in d orbital. So j is 5/2, L is 2, S is 1/2. So obviously it is a case of L plus S, that is the stretched case, and stretched case we will find out for neutron. So this is the last unpaired neutron. So we will use this formula. Mu comes out to be minus 1.19 times mu n, and the value of this magnetic moment that we know from this formula. So mu is equal to, this is nuclear magnetron, this is G, and this is J. So that is equal to minus of 1.91 times nuclear magnetron. So they get cancelled out, and from that you can find out the value of this G factor. So this G factor, it is different for proton and for neutron, and it comes out to be minus 0.77. So for this question, correct option is option B. So what are the limitations which has been not overcome by the shell model? So it has been explained by this collective model. Now collective model, so if you look at this, many quadrupole movements, so they are having larger value as compared to the predicted value. So these are some of the quadrupole movements, so whose quadrupole movement value, that is by the shell model, it is coming different, and these are the experimental value. So this quadrupole movement, why the value of this quadrupole movement it is coming different, it has been explained by this collective model. Now the collective model, it is made, or it is being designed by J. Rainwater in 1950. So who combined these two models, liquid drop model and shell model, and he suggested a new model that is known as the collective model. And he said that the nucleons, so they are moving collectively. So it is due to the collective motion, which is there is occurrence of this deformation, and due to this deformation there is some sort of oscillations and rotation which exist within these nucleons. So in net nuclear potential, so which we have considered in shell model, that the nuclear potential it is fixed. Here the collective model says that this net nuclear potential, due to the consistent motion of these nucleons, because these nucleons, so they are vibrating within these nucleus, they are rotating within these nucleus. So this net nuclear potential, it is changing time to time. So due to this changing nuclear potential, so there is a change of this radius of this nucleus. So this radius of this nucleus, it is no longer a fixed throughout the motion of these nucleons, and he derived that this radius, it is basically dependent upon three type of energies. So the total energy of this nucleus, it is sum of the vibrations energy, sum of rotation energy, plus sum of the nucleonic energy. So the interaction between this outer nucleons and core nucleons, so they lead to permanent deformation of this potential. So this deformation, it represents the collective motion of nucleons in the core, and they are related to liquid drop model. So he combined these two models. So he used the concept of liquid drop model as well as the shell model, and he explained this model. So he explained this model in two forms. So he said that, so the collective motion of these two type of nucleons. So one are core nucleons. So these are those nucleons whose octet is completely filled, and other nucleons, so they are the valence nucleons, so which are present in the outermost shell. So these rotations and vibrations, so they are due to this core nucleons, and the deformation, it occurs due to this valence nucleons. So he explained separately the concept of this vibrational energy spectra of these nucleons and the rotational energy of these nucleons. And so let us discuss separately. So he said that the total energy of these nucleons, it is sum of rotational energy, vibrational energy plus nucleonic energy. Now this collective motion of this nucleon core, it gives rise to rotational and vibrational terms, and the nucleonic energy term, it is the motion of these valence nucleons or the loose nucleons, and they are due to this nucleonic energy. So there are various four important motions which exist within this nucleons. So one is the surface vibrations. So if you can see that, so these are the nucleons which are present in the outermost shell. So they are moving in the shell, and due to their motion, so the motion of these nucleons, so it is changing the shape of the nucleus from spherical to the deformed nucleus. So there are some sort of vibrations which is happening within the nucleons, and due to these surface vibrations, the shape of this nucleus, it is continuously changing. So second, he said the concept of compression and rarefaction. So it is something like, suppose some neutrons, they are moving inward, protons, they are moving outwards, and due to the opposite motion of this neutron and proton, and which is causing this compression and rarefaction of this spherical nucleus, and that's why this nucleus sphere, it is changing its shape time to time, and this is the oscillation of this deformed nucleus. So what he has considered that the nucleons which are present in this core, so they are acting like a semi-fluid, and these outer valence nucleons, so depending upon the number, so due to this outer nucleons, so they are moving in the outer core, and due to this oscillation, so there is the deformation of the nucleus, and he has found that the circular frequency of this core nucleons, so that is less as compared to their valence or the outermost nucleons. So there are something like deformation, something like surface vibration, something like compression and rarefaction, which is happening due to this motion of neutrons and protons. So it is against the shell model. Now shell model says that, so it is considering only the last unpaired neutron on proton. So the last unpaired neutron on proton, it is finding out the magnetic moment based on this unpaired neutron. it is finding out the quadrupole movement based on this unpaired neutron. So the collective model says that it is not only the last unpaired neutron or protons, so there are nucleons which are the core nucleons, although they are even or although they are paired up, but they are also playing the role of some quadrupole movement or some magnetic movement in changing the magnetic movement of the nucleons, because they are not fixed. So these, even though their core is filled, but they are not fixed within the nucleus, so they are continuously moving, they are undergoing some sort of vibrations, and they are undergoing some sort of rotations, and their rotational and vibrational energy, so the same as we study in this atomic spectra, so it is being changing. And based on that, he find out, he derived a model, and from that model he find out why there is a monopole, why there is the dipole movement, why there is quadrupole movement, why there is octopole movement. And based on that, he find out the first excited state, second excited state, and how the higher excited states which are present within this nucleus. So these are some of the model which has been explained by this J. Rainwater. I will not go in detail. So the basic idea is he find out the value of this radius, and based on this radius he find out the moment of inertia, and from this moment of inertia he find out the total angular momentum, and from that he says that these oscillations, they are quantized, and the vibrations, so they are something like a phonons. So phonons are those particles, so as the electromagnetic energy waves, so it is quantized due to the presence of photons, and the energy is being exchanged from one point to another point, so due to the exchange of this photon. So similarly, so this energy within the nucleons, it is exchanged due to the exchange motion of phonons. So this is quantized particles which are present within this nucleus. So you can see from that, so even though for the even nuclei, so it is the harmonic oscillator according to shell model, it is saying that it should be something like that, but according to this collective motion, it is seeing that there is some sort of deformation which is also present, even though the nucleons, they are even nuclei. So this diagram, it is representing how the shape of this nucleus, it is continuously changing due to this change in the radius of this nuclei in the 3 dimensions, and this average shape of the nucleus, although it is a spherical, but its instantaneous shape, it is not spherical, and its shape, it is being changing depending upon how the neutrons and protons, so they are interacting within this nucleus. And he calculated this, how the nucleus, it is changing its shape. So he calculated from the concept of this isospin. So nucleons, it can vibrate in 2 ways. So if the protons and neutrons within the nucleus, they are moving in the same direction, then he calculated the total isospin, it comes out to be equal to 0, and that he given the name isoscalar nucleons. And if the proton and neutron, they are moving in opposite direction, then the total isospin, it is equal to 1, and that is known as isovector. So based on this concept of isospin, he designed various vibrational modes within the nuclei. So when the quantized particle, when the lambda is 0, that is in the ground state nuclei, so there are some sort of radial vibrations only, and that is known as the monopole. So here you can see that the proton and neutrons, so they are moving in the same direction, that is toward the center of the nuclei, and this is something like a monopole. And if the proton and the neutrons, they are moving opposites proton are present within the center, while neutrons, they are moving in the outer valence nucleons. So then it is something like this. So again he said there is the dipole. So why two poles? So sometimes we look at that the shape of the nucleus, it is something like it changing from its original position, and that is due to this isoscalar modes, because the neutrons, they are moving in this direction, and the proton within the nucleus, they are moving in this direction, and due to the opposite motion of this neutron and protons, so this nucleus, it is something like acting as a dipole or acting as a magnet. So because the particles, they are at the opposite end. So similarly, you can see that the nucleons, it is something like a prolate shape, and after some time it changes its shape and it becomes oblate, and that is due to the quadrupole movement. So this quadrupole movement, again, it is due to the isoscalar and isovector concept. So how the proton and neutron, if they are moving in same direction or moving in opposite directions. So based on these vibration modes, so he calculated different energies of these different excited states. So he said that there are some sort of giant resonances, and the resonance means that the nucleons which are present, either they are core nucleons or either they are the valence nucleons, there is some sort of resonance, some sort of interaction which is being happening between this proton and this neutron, and due to this giant resonances, there are different types of excited states which are present, or there are different vibration modes which are present, and based on these vibration modes, we can see that some nuclei, so they are having different energy as compared to the other nuclei. So this giant dipole or the giant resonances, they are observed experimentally as in many nuclei. So the position of this giant resonances, depending upon the excitation energy and depending upon the mass of this nuclei, so this giant resonance, it is different for different nuclei. So this is the concept of giant resonance. I will not go in detail. So this is showing that the collective behavior, which is the nuclear, how the photonuclear giant reaction motion, that is the electric field of photon which is acting on this protons or neutron, and due to that the protons which are moving in the center of mass, or they are at rest, while the neutrons, they try to move in the opposite sides, and due to this motion of protons and neutrons towards the opposite end, so there is some sort of resonance force, some resonance interaction, and this resonance interaction which leads to different multipolarities of this nuclear phenomena, and this giant resonance, it can be the electrical resonance depending upon how the parity of the initial and final state nuclei, it is being changed, and it can be calculated as whether this resonance, it is due to the magnetic effects, and that we can also calculate from -1 L plus 1. So depending upon how the angular momentum, how the value of this L, it is being changed when these proton and neutrons, so they are changing their orbital from ground state to excited states. So this is how the outermost particle, like the photons, when they are trying to interact with these nucleons, and this giant dipole resonance concept we will discuss more in detail when we will discuss gamma decay. And because in gamma decay that concept is more in detail, it can explain whether the gamma ray emission, it is a electric emission or it is a magnetic emission. So the same concept they have applied here, and due to this giant resonances, So this there are some sort of vibrations which is being started within these nuclei. So this is how they have find out for the monopole. So when the neutron and proton they are moving opposite, and how the value of this radius it is being changed. And so for this case they have considered there is only radial vibration, and this is known as the ground state energy state, that is the phonon number will be equal to 0. And for dipole vibrations, so this value of lambda that is equal to 1, and this is generally known as the first excited state. And in this dipole vibration you will see that the value of this radius it is continuously changing, as due to this Ligure polynomial they have applied here. And similarly they have experimentally calculated that the energy of this giant dipole resonant it should be compared with the shell model, and they have found this much of difference in energy as compared to the shell model. And these values they are more close or more satisfied as compared to experimental results. So they have experimentally proved how the photo disintegration spectrum of this gold it is being happening. And the gold atoms they are when bombarded with high energy gamma radiations, and they are emitting some sort of neutron. And this neutron emission that is due to this giant dipole resonance you can see from this graph. And from this experiment it proves that the giant dipole resonance, giant quadrupole resonance, or giant octopole resonance, so there are some sort of resonance which exist how these nucleons it is interacting with these outermost particles. So similarly you can find out with the quadrupole movement how the nucleons it is being deformed continuously. So these are some of the slides which will give you flavor that how the shape of this nucleons it is continuously changing depending upon how many nucleons it are present within the core nucleon, depending on how many nucleons which are present within the outermost shell. So based on that, so they undergo deformation, compression and rarefaction, so and so. So from that we have considered the harmonic motion or harmonic oscillator model, and they find out that the angular frequency it is depending upon these two parameters. And this C parameter that is known as the deformed parameter, which is telling how much deformation it can happen, and it is due to this kinetic energy. So you can see that this deformed parameter B it is directly related with the kinetic energy of these nucleons. B parameter is deformed parameter, and this C parameter that is related with this potential energy. So C parameter is known as the restoring force. So restoring force, how these nucleons when they are interacting, and how the value of this C it is being changed, and based on this B and C constants, so the angular frequency of this nucleons it is being changed continuously. So from this angular frequency they have find out the total energy for different states. So here n that is representing the lambda. So what is, whether it is a ground state nuclei, it is a first excited state, it is a second excited state, so and so. So they have found that for ground state nuclei, so when lambda, in some books the notation is written n, in some books it is written lambda. So that is the degree of phonons. So when lambda is 0, then energy is of 0, and there is only one ground state possible, that is 0 plus. When lambda is equal to 1, that is the first excited state, so then there is only one state which is possible, that is 2 plus state. And when lambda is 3, lambda is 2, there are two phonon triplet states which are possible. 0 plus, 2 plus, 4 plus, and by removing these perturbations, they have found that the value of all these three states, they are almost same. So the same way how these nucleons, so they are interacting and how they are changing their energies, and there are some vibrations when the value of this lambda that is greater than or equal to 3, and that is known as the octopole modes, but they are not so much observed experimentally. So we will not talk this is because this is a more complex phenomena. So when lambda is 4, so then the nucleus structure, it is something like this. So the nucleus, it is changing how many vibration modes they are undergoing. So in deformed nucleus, there is not only the vibrations, but also the rotational states are possible. So the rotational states, how the due to this rotational states, so the how this nucleus, it is continuously changing its shape from oblate to prolate, and so this rotation, they are associated due to this valence nucleons which are present in the outermost shells. So nuclear rotations, so they have also find out the rotational energy spectra, and they found out the energy of this rotation, and this is due to the rigid rotator, and the value of this R, it is being continuously changing due to this nuclear rotation, and I is representing the moment of inertia. So this is the formula which you will use in order to find the different energy rotational states, and some numericals, they also comes from this portion. So these are some of the uranium-238 rotational energy levels. They have found out how the energy and the gap, it is being increasing continuously. So as they are moving towards this excited states. So once you find out the energy of one state, then it is easy for us to find out the energy of any other state using this formula, because the value of this h square over 2i, so that we can find out, and using this formula we can put this value and we can find out any energy state of any nuclei. So this is all about the collective model, and how using this nuclear vibrations and rotations, they have explained about the various unfold results, like why the quadrupole movement, it is very much different for nuclei, and they have compared experimentally, and this model is very successful as compared to shell model. Now this question is, a permanent deformed even nucleus with spin Jp that is equal to 2 plus has rotational energy of 93 keV. So what is we have to find the energy of this excited state. So let us say, so for 2 plus state, so the energy is being given. So let me draw here. So for the ground state, it is having 0 plus. For first excited state, so that is. So here I would like to tell you that for the rotational energy, so there is only the J value. So even J values, they are only allowed. Even values are allowed. So for 2 plus, they have given that the energy is 93 keV. Then the energy of the next excited state. So next excited state, that is 4 plus state. So we have to find the energy of this state. So for the rotational energy spectra, so the energy formula is Aj, that is equal to h square over 2I. So here I is the moment of inertia J plus 1. So here J is 0. So here J is 2 plus. So this is given 93 h square over 2I when J is 2. 2 plus 1. So this comes out to be h square over 2I, that is equal to 93 over 6. So for next state, that is this 4 plus state, we have to find the energy value. So here J will be equal to 4. 4 plus 1. So it comes out to be h square over 2I, that is equal to 93 by 6 into 4 into 5. So you can calculate from here 2, 3, 2, 2, 3 into 31. So 62 into 5, so that is equal to 310 keV. So the energy of this 4 plus or the second excited state, so that will be of the order of 310 kilo electron volt. So, and this is the question of NET June 2014 examination. So this is all about for today's lecture, and I think we have almost covered all those topics of the models or the nuclear models which are present in your syllabus in NET GATE examination, because otherwise there are many other model discoveries which we can discuss, like the Nielsen model or the unified model or the Fermi gas model, which is quite successful because in that model they have considered that the nucleons, they are acting as the Fermi gas, and you based on these they find out the Fermi gas derivations. So but we will not go in that detail because they are not part of your syllabus. So this collective model and shell model and liquid drop model, so these are the three models so which we have covered in detail. And if you have any question related to today's lecture, you can ask.